The day Earth almost died. The apocalypse worse than the asteroid. When we think of mass extinctions, our minds almost instinctively jump to the end of the Cretaceous period, about 66 million years ago. We picture the flash of light, the Chicxulub asteroid impact, and the dramatic end of the non-avian dinosaurs. It is a cinematic ending to a reptilian dynasty. However, in the grand library of Earth's history, the asteroid impact is merely the second worst chapter. To find the true horror story, the one that keeps paleontologists awake at night, we have to travel back much further, to 252 million years ago. We are journeying to the end of the Permian period. This was a time before the dinosaurs ruled, a time when all the world's landmasses were smashed together into the supercontinent Pangaea. It was a world of vast deserts, strange mammal-like reptiles, and thriving oceans. And then, in a geological blink of an eye, it almost all ended. This event is known as the Permian-Triassic Extinction event, but scientists often refer to it by a more somber name, the Great Dying. The statistics are terrifying. It is estimated that 96% of all marine species and 70% of terrestrial vertebrate species vanished. It is the only known mass extinction of insects. It was a slaughter so comprehensive that it set the evolution of life back by millions of years. The question that has driven scientists for decades is simple. What could possibly kill nearly everything? For a long time, the culprit remained a mystery. Was it a supernova? A massive release of methane from the seafloor? Another asteroid? Through decades of forensic geology, analyzing rock layers and chemical signatures from China to Russia, the scientific community has largely converged on a suspect. The killer was not a visitor from outer space. The killer came from within, the Siberian traps, a volcano unlike any other. To understand the Great Dying, we must look to modern-day Russia, specifically the region of Siberia. Buried beneath the snow and forests lies a geological formation known as the Siberian Traps. Today, it is just rock. But 252 million years ago, this was a wound in the Earth's crust. We are not talking about a standard volcanic eruption like Mount St. Helens or Vesuvius, which are violent but localized. We are talking about flood basalts. Imagine a tear in the planetary crust that oozes lava not for days, but for hundreds of thousands, perhaps millions of years. The volume of lava produced was staggering enough to cover the entire continental United States in a layer of rock half a mile deep. But lava alone does not kill 96% of marine life worldwide. If you are a trilobite living on the other side of Pangaea, you do not care about lava in Siberia. The lava was merely the trigger. The true weapon was the gas. The atmospheric collapse as the Siberian traps erupted. They released colossal amounts of carbon dioxide and sulfur dioxide into the atmosphere. This marked the beginning of a runaway greenhouse effect. Global temperatures skyrocketed. The sulfur initially blocked the sun, causing a brief volcanic winter. But as it settled, the CO2 took over, trapping heat. Isotope analysis of tooth enamel from conodonts, eel-like creatures of the time, suggests that tropical ocean temperatures rose to nearly 40 degrees Celsius, 104 degrees Fahrenheit. At these temperatures, basic biological functions begin to fail. The planet was running a fever that it could not sweat out. This heat triggered a chain reaction. As the oceans warmed, they lost their ability to hold oxygen. Warm water holds less gas than cold water. The deep oceans became anoxic, meaning completely devoid of oxygen. It was a suffocation event on a planetary scale. But the horror did not stop there. The toxic oceans and the pink sky deep in these oxygen-starved waters, a new threat emerged. Bacteria that thrive in anaerobic conditions began to bloom. These bacteria produce hydrogen sulfide, a gas that smells like rotten eggs and is lethal to most aerobic life. Models suggest that huge bubbles of this toxic gas rose from the depths, poisoning the marine life that was clinging to survival in the shallows, and then entering the atmosphere too. Poison animals on land. There is a hypothesis that during this time, the oceans would have turned a sickly purple due to the sulfur-loving bacteria, and the sky would have turned a hazy green. Acid rain, caused by the sulfur in the atmosphere, would have scoured the land, stripping forests of their leaves and turning soil into mud. We see evidence of this in the fungal spike, in rock layers marking the boundary between the Permian and the Triassic. There is a sudden abundance of fungal spores. Why? Because the world was full of dead trees and decaying matter. The forests had died, and fungi were the only things thriving on the rot. The victims of the great dying, the biological cost was incalculable. The Trilobites, those iconic armored arthropods that had scurried across the ocean floors for nearly 300 million years, were finally extinguished. They survived 2 previous mass extinctions. But the great dying was too much. On land, the dominant animals were the synapsids, often called mammal-like reptiles. These included the fearsome Gorgonopsids' apex predators with saber teeth. They were wiped out. The large herbivores, the parasaurs, were also decimated. The complex ecosystems of the Permian collapsed into dust. The extinction of insects is particularly telling. Insects are incredibly resilient. They usually survive everything. But during the Permian extinction, nearly a third of insect orders were lost. This suggests a catastrophic collapse of the plant life they relied on, combined with an atmosphere that may have been chemically hostile to their respiration. The long recovery, what is perhaps most chilling about the great dying, is not just the speed of the destruction, but the slowness of the recovery. After the asteroid killed the dinosaurs, life bounced back relatively quickly in geological terms. But after the Permian extinction, Earth remained a wasteland for millions of years. The early Triassic period, which followed, is often described as a coal gap. We find no coal deposits from this era because there were simply not enough forests to form them. The planet was hot, dry, and barren. For a long time, the land was dominated by a single genus of animal, Lystrosaurus. It was a pig-sized, burrowing herbivore that somehow managed to survive the apocalypse. For a few million years, if you walked across Pangaea, Lystrosaurus was essentially the only large animal you would see. It is a stark reminder of how low diversity had fallen. The legacy of the catastrophe, however, as the saying goes, nature abhors a vacuum. The emptiness left by the great dying created an evolutionary opportunity. With the dominant competitors of the Permian gone, the surviving reptiles began to experiment with new forms. Among these survivors were the archosaurs. In the recovery period of the Triassic, they diversified rapidly, eventually splitting into 2 main lineages, the ancestors of crocodiles and the ancestors of the dinosaurs and birds. It is a strange irony that the greatest catastrophe in the history of life paved the way for its most famous era. Without the great dying clearing the stage, the dinosaurs might never have risen to dominance. The Gorgonopsids might have continued to rule, and the evolutionary path that led to mammals and eventually to us might have looked very different. A warning from the past, studying the great dying is not just an exercise in ancient history. It is a cautionary tale. The mechanisms that caused the Permian extinction, rapid release of greenhouse gases, global warming, ocean acidification, and deoxygenation, are the exact same phenomena we are observing today, while our current rate of carbon emissions is happening over decades rather than millennia. The chemical principles remain the same. The Siberian traps released gigatons of carbon into the atmosphere, tipping the Earth's systems into chaos. By studying rocks from 252 million years ago, scientists hope to understand the tipping points of our own climate system. The Great Dying serves as a monument to the fragility of life. We often think of the Earth as stable and enduring, but the Permian-Triassic boundary proves that the biosphere can be pushed beyond its breaking point. It shows us that life is resilient. Yes, life did not disappear completely, but the civilization of species that exists before a tipping point is rarely the one that survives to see the recovery. Conclusion, the story of the Great Dying is a story of fire and ice, of poison and persistence. It stands as the darkest hour in the biography of our planet. It was the moment when the lights almost went out forever. Yet, from the ashes of the Permian world, the modern world was born. Every animal alive today is a descendant of the ragtag band of survivors that endured the acid rain and the purple oceans. We carry the legacy of that survival in our genes. We are here only because, against all odds, life found a way to hold on when the world turned into a HELLSCAPE. Understanding this event changes how we look at the ground beneath our feet. It reminds us that we are living on a planet with a violent temper, capable of resetting the game board completely. It is a history written in stone, warning us that while life is tenacious, it is not invincible. Thank you so much for watching all the way to the end. If you enjoyed this video, learned something new, or simply want to see more content like this, please give it a like and subscribe to the channel. Your support truly helps the channel grow and reach more people. And if you have thoughts or ideas you'd like to share, feel free to leave a comment. I'd love to hear from you. See you in the next video.